All right, so I guess some questions during the break, which we can just go over with everyone. So here, the parameters A and B, we get to choose A and B. So I guess the tricky part of Bayesian inference is you get to choose what sort of prior you want to use. And that choice of prior isn't immediately obvious. In some sense, we're like, rather than just estimating theta directly, we're moving up a level of abstraction and choosing the parameters for the prior. And I guess it's just like your belief on what the world state is before flipping any of the coins. And if we were to look back at this graph, just to make sure we understand what the different thetas correspond to, this is theta MLE, this is theta map, and then the third possible estimator you can use is you can take the expected value of the posterior. So we take the expected value of the red curve. So that's three potential ways you can estimate your parameters. So I guess one special case of priors is if you choose A equals B equals 1, that's sometimes called the Laplace prior. And it's basically assuming that you just have one observation of everything you've seen so far, and maybe that's a good default choice. So we have a special name for it. Okay, are we ready to do some multivariate Gaussian stuff? So the motivating example is we're going to consider the setup here where we're trying to maybe predict whether a patient coming in has diabetes or not. So you might take measurements of their white blood cell count and their glucose value. And you have a bunch of historical data on given these two quantities, whether a patient has diabetes or not. And you can sort of see that we have two natural clusters here. So in the previous setups, like for a logistic regression, we would just try to find the decision boundary directly. What we're going to do now in this lecture is we're going to try to model the distributions over the two data sets. So perhaps the mean of the green points is somewhere here. We can estimate the contours of the green plot. And we can also do the same thing for the red plot. So the overall overarching idea is we're still going to focus on a generative model where we sort of estimate what each individual class looks like. So to get to that point, we'll do some linear algebra review, and this will also help us when we talk about principal component analysis next lecture, which will be a unsupervised learning algorithm. So a lot of the math background here, the Math for Machine Learning book can cover in more detail and has some additional exercises. In this lecture, we'll do some review of linear algebra. Then we'll talk about how you actually model and how you should think about multivariate Gaussians. And I guess there's some other map MLE stuff we can do. Like we already did one of the exercises here, which is finding the maximum likelihood estimator of a univariate Gaussian variable. Okay. So the really important thing, I guess, to note here is the idea of eigenvectors and eigenvalues. So hopefully most of this isn't completely new, but we'll try to take more of a geometric understanding of some of these concepts. So the definition of I guess if we view B as a square matrix, B is applying linear transformations to different vectors, right? So in general, if you have some vector V, and you apply b to it, it's going to move the vector v somewhere else into the space. So it might move it here. So the vast majority of vectors end up being pointed in different directions from where they were originally pointed. But we have these special vectors, which we refer to as the eigenvectors of a particular matrix or a linear transformation, which stay in the span of where they originally were. So they either get squished or they get stretched out, or potentially flipped and stretched out. So these special vectors are called eigenvectors. And if v was an eigenvector, it would lie somewhere along this line. So bv is in span if eigenvector. And there's some great videos online on how the stretching interpretation works. You can visualize all this in more detail. In general, a matrix of size d by d has at most d distinct eigenvalues, sometimes fewer. And in the context of this course, we'll primarily just focus on symmetric matrices because we can say more things about the eigenvectors and eigenvalues they have. So the spectral theorem, which is a theorem we'll use but we won't need to prove, is it says for a symmetric d by d matrix, all of the eigenvalues are actually going to be real valued, and we can actually find a set of linearly independent eigenvectors, which are real valued and form an orthonormal basis. So what that means is we can find v1, v2, all the way to v sub d, where each of these are eigenvectors. And we have vi transpose vj equals 0 if I not equal to j. So all the vectors are mutually orthogonal to each other. And vi transpose vi equals 1. So what that means is you can actually just stack all of these into one single matrix. So if we called this the V matrix, V1, V2, Vd, what is V transpose V going to equal to? If we know that the V vectors have these properties. Yeah, it's going to be the identity matrix, because essentially you can think of V transpose V as actually doing exactly one of the eigenvectors times another eigenvector. So it's going to be 1 on the diagonals and 0 everywhere else. Yeah.
In this case, do we consider V as rows of the vector entries or columns as vector entries?
In this case, we're considering them to be columns. Yeah, I think usually you think of them as columns. So list decomposition exists. I guess in general, if you were actually to find the eigenvectors or eigenvalues, you might remember from a previous class, you would move all of this to one side. So you would do b minus lambda I, v equals 0. And then you take the determinant, you get some characteristic polynomial, and then that can help you find the eigenvalues. From there, you can find the eigenvectors. And it's sort of a mechanical procedure, which we won't do much in this class, but you should know such a procedure exists. So in general, what we do when we have a symmetric matrix is we can express it in this really convenient form, Q lambda Q transpose. And this Q matrix is going to be our matrix of eigenvectors. So each of the columns is an eigenvector. Let's use n here. And then lambda is a diagonal matrix with lambda 1, lambda 2, and Q transpose is you're flipping everything around, so Q transpose right here. And we can check that this definition makes sense. So assuming you have these eigenvectors and eigenvalues, which we know we do by the spectral theorem, you can write A times Qi is going to equal lambda I Qi. So if you were to repeat this in matrix form, you can write like Q1, Q2, all the way to Qn. And that's equal to this diagonal matrix, lambda 1 times Q transpose. Times Q itself. Right. So essentially you can rearrange and you should be able to get the spectral decomposition. The actual geometric interpretation of what's going on here is if we have this eigenbasis, the Q transpose matrix is rotating everything into this eigenbasis, and then lambda is scaling each of the components accordingly by the lambda values, and then the Q matrix is rotating back to your original basis. So you can view the operation A as being decomposed into 3 separate operations as well. Right. So I guess this describes what I said again. So if you apply Q transpose to a vector, this converts to eigenbasis. And then applying Q converts back to your original basis. So what that means is like if you're applying A to X, you can also view it as A applied to each of the eigen vectors scaled by the coordinates of those eigenvectors. And then when we're dealing with Lee's matrix, we have a few other terms to refer to the corresponding to the eigenvalues of the matrices. So remember from before, we said this function f of v equals v transpose av is something called a quadratic form. And if v transpose av is always positive for any v not equal to 0, we call that positive definite. And you should think of that as a bowl-shaped function where in every direction the function is increasing. So that's pictured over here. We have 2 potential ways to visualize it. You can visualize it in 3D where every direction it's increasing. Or you can draw the contour plot where the contour lines denote where the value is equal. We also have positive semi-definite, which is the same definition, but we have greater than or equal to 0. And for both of these terms, we overload the terminology a little bit. So rather than having a normal greater than sign, we have a squiggly greater than sign. So if the matrix on the left has a sign, you should note that means positive definite. Similarly, you have a definition for negative definite and also indefinite where we can't say anything about the value of V transpose AV. So positive semi-definite here, I guess focusing on this graph over here, says there's one direction where the function might be 0. So this direction, the function equals 0. but there's other directions where the function value can potentially increase. So these are just some definitions we need to cover the topic of multivariate Gaussians. Okay. So let's do some exercises. The first one is non-negative linear combinations of PSD matrices are also positive semi-definite. So let's just focus on the example with two things. So we have A greater than 0 and B greater than 0. Your goal is to prove that A plus B is greater than 0. And then the second exercise is for any matrix B, you want to show the matrix B, B transpose is also positive semi-definite. I'll actually add a third one here. So third exercise is what are the eigenvectors and eigenvalues for A inverse? So assuming you know the eigenvectors and eigenvalues for A, can you find a simple expression for what A inverse looks like? Yeah.
Shouldn't it be the thing with the line underneath it because it's positive semi-definite?
Yeah, good point. Okay, but the same property holds if everything's positive definite actually. So you would just have greater than signs. But yeah, for this exercise, let's use greater than or equal to. Let's take 3 minutes or so, think about it yourself first, and then we'll discuss together. Or yeah, feel free to talk to the people around you as well. Okay, I realized I made a mistake on the previous slide, so these two have to be rearranged actually. So if we write it out again, it's going to be Q1 I guess matrix multiplication is a little bit tricky to try to picture how the vectors and matrices hit each other. But if you write out an example, you should see that this matrix form that we wrote on the bottom is exactly corresponding to each of the equations up top. So if you go back to this here, we have A times the matrix Q is equal to Q times the matrix lambda. And this lets you factorize Q because by definition we have Q transpose Q equals I. So Q and Q transposes are actually inverses of each other. It's a really convenient property where you can just transpose a matrix to invert it, which means if we want just A on one side, we can right multiply by Q transpose. So AQ Q transpose equals Q lambda Q transpose. So that's what we refer to as the eigen decomposition. All right, so let's go ahead and do these exercises together. So for A inverse, let's start again from AV equals lambda V. How do we get A inverse into this equation? So let's say lambda and V are eigenvectors and eigenvalues for A. Yeah. Yeah, great. So we hit most sides by A inverse. We have A inverse lambda V. Lambda is a scalar, which means you can interchange the order of the matrix, doesn't really matter. And we have V equals lambda A inverse V. And you can divide both sides through by lambda, right? So we have 1 over lambda V is equal to A inverse V. So what this is saying is the eigenvalues of A inverse are 1 over lambda 1, 1 over lambda 2, all the way to 1 over lambda n. And the eigenvectors are exactly the same as well. Conceptually, this should actually make sense because if A is increasing the dimensions by lambda 1 in the first eigenvector direction, lambda 2 in the second direction, and so on, if we want to invert the operation, we just shrink by a corresponding factor. Right? So we do 1 over lambda 1 in the first direction and 1 over lambda 2 in the second direction. So.
Can we just assume that the inverse exists because it's a square matrix?
Yeah, I guess assuming it's invertible, so like assuming we don't have 0 eigenvalues, then yeah. That's what the inverse is. Okay, let's do second exercise. So non-negative linear combinations are positive semi-definite. So here, by definition, we know for all x transpose AX is greater than or equal to 0, and x transpose BX is greater than or equal to 0. So checking the definition actually is relatively straightforward. So for a new x, we look at x transpose A plus B times x, and that's equal to x transpose AX plus x transpose BX. So that's greater than or equal to 0. And in general, if you have more positive semi-definite matrices, we're just going to get a whole bunch of terms that are all greater than or equal to 0, and you can scale them by non-negative constants as well. The property is still going to hold. So a generalization of this is saying if you have a random matrix where every possible instantiation of that matrix is positive semi-definite, then the expectation of that random matrix is also positive semi-definite. Okay, so that's the first property. The second property that we sort of deal with when we're talking about Gaussians later, is for any matrix B, we want to show B transpose is positive semi-definite. So the way we do this is we consider some x, x, and then let's look at what x B transpose x is. Yeah.
Should it be X transpose B, B transpose X?
Yeah. Okay. Yeah. What do you?
Then we have B transpose X transpose B transpose X.
Yeah. Great.
That's just the norm of B transpose X, which is always constant.
Yeah.
What we're
Yep. That's good. So yeah, in general, the property we're using is if you're transposing two things, the product of matrix and a vector, I guess, it's going to equal B transpose A transpose. So you flip things around. And if we do that here, we have the first part of this expression as B transpose X transpose. Second part of the expression as B transpose X. And this is actually just in the form C transpose C, right, which we talked about before. That's equivalently written as the norm of C, 2 norm of C squared. So we can write this term up here as B transpose X 2 norm squared. And norms are always non-negative, so greater than or equal to 0. So in general, this says that if you see the product of a matrix and its transpose, we know that's a positive semi-definite matrix. So later, the covariance matrix is also going to be positive semi-definite. Okay. Yeah, I guess there's actually a third property that's pretty important, which is if A is positive definite, that implies all of its eigenvalues are positive and vice versa. Intuitively, you can sort of see this in the picture here. For the positive definite matrix, in every single direction, the function value is increasing, which means if you do have an eigendirection, the value is positive as well. Right? So that's a geometric intuition. But we can also prove this mathematically as well. The way we do that is we look at the eigen decomposition, V transpose AV. We can write this as V transpose Q lambda Q transpose V. And we're going to define V transpose Q and Q transpose V as, we'll define Q transpose V as some other variable. Let's call it W. So this gives us let's call this W. So this gives us W transpose lambda W. And if you have a diagonal matrix in the middle and this quadratic form expression in terms of W, it's actually going to be exactly equal to the summation of lambda I Wi squared. Remember, I guess that in one of the lectures we wrote out the formula for the quadratic form, and it's exactly equal to how the two terms are correlated, essentially, by the matrix in the middle. And since the matrix in the middle is diagonal, we don't have any cross terms. So this is a summation from I equals 1 to n. And essentially what this property is saying is if we want this entire expression to be non-negative for every single possible W, then we must have each of the lambda values has to be non-negative as well. So yeah, that's just another property for positive definite matrices. Any questions here? Okay, let's try to picture a few of these because we'll see how this relates to the geometry of multivariate Gaussians pretty soon. So if A is positive, definite, and diagonal, it's actually going to be exactly axis aligned, meaning each of its main axes is parallel to the x or the y axis. That's because if we have this A matrix like here, we can write this as 0.5 x1 squared plus x2 squared. And if you remember like the definitions of ellipsoids, this is actually going to be like exactly a axis aligned ellipsoid. Like you can draw out like what each of the contour lines looks like. But in general, the axes are going to be aligned to the directions of the eigenvectors and eigenvalues because those are the directions where scaling, like things just scale naturally. So in this case, we have a non-axis aligned quadratic form. And in this sense, like all symmetric matrices are going to be diagonal if you look at the coordinate system of the eigenvectors. And then a few other linear algebra concepts. So in general, if you were to take a matrix to the 100th power or something like that, it's really hard if you try to do it naively, like multiplying one matrix by another one at a time. But so the trick we generally do when we have this a to the 100 term is we're going to shift things to the eigenbasis, because in the eigenbasis, matrix exponentials just become exponentials of each component of the matrix. And that has a nice interpretation. So in particular, if you have a squared, for instance, we end up with Q lambda Q transpose Q lambda Q transpose. If you were to interpret this operation on some vector x, what this is doing is it's shift to eigenbasis then you scale by eigenvalues. So that's a lambda. And then you keep going, right? So the Q shifts back to your original basis. And then you shift 2 again. So the definition of the inverse is actually quite a nice geometric interpretation. It's saying we're shifting back and forth between our eigenbasis. Then we scale again, and then finally we shift back again. So this net effect is the identity, and then in effect what you're doing is you're just scaling by the eigenvalues twice. And you can imagine if you apply this transformation 100 times, all the intermediate shifting back and 2 from the system go away. So what you're really doing is you're just shifting the eigenbasis once, scaling by whatever power you care about, and then shifting back. So a to the 100 is just going to be Q lambda to the 100 Q transpose. We covered how the inverses work. So the eigenvectors are the same, but the eigenvalues get inverted. And this also allows us to define the notion of a square root of a matrix, which we need later on. So the idea of a square root is a matrix where we want a to the 1/2 times a to the 1/2 to equal a. So the way you do that, because we know, so assuming a matrix is positive semi-definite, you can take the square root of the diagonal entries. So when you square it again, you'll get a back. Some determinant properties. I think the one up top here is probably one you'll occasionally see. So in general, the product of a matrix, if you take the determinant of a product of matrices, it's going to be the determinant of each individual matrix, and then you take the product of those. So what that means is for Q lambda Q transpose, you can decompose it into this form. And we can actually group the Q transpose and the Q together again. So this will be lambda Q transpose Q. Q transpose Q is identity, right? So we have lambda times 1, because the determinant of identity matrix is 1. So what that means is the determinant of a matrix in general is actually just the product of its eigenvalues. And intuitively, a determinant you can sort of think of as a volume, like how voluminous a matrix transformation is. Yeah, I think the rest of these properties we'll just use them if we need them. I don't think we necessarily need all of them. Okay, so that's a good amount of linear algebra review. Now we'll return back to the idea. First, we'll briefly cover the univariate Gaussian distribution again. For this term down here, you often see it written as 2 pi sigma, or you could put the sigma squared in the square root as well. And that's our formula for the Gaussian distribution. It's really popular because it shows up in many different contexts, and the math involving Gaussians is relatively easy. So we like to model distributions as Gaussians if we can. The central limit theorem says that if you add up a bunch of independent random variables, then you get approximately a Gaussian curve. So I guess if you look at the distribution of heights in a population, or distribution of exam scores, where the scores are the sum of a bunch of different questions, the scores usually tend to follow a Gaussian distribution, which is why we like to use this modeling choice. The key term to focus on when dealing with Gaussians is really this term over here, because this is the probability, this is like proportional to the probability density. And it's maximized at mu. So because we have a negative in the exponent, it's going to be progressively smaller, the density, as you move away from mu. The 1/2 pi sigma squared just makes sure if you integrate this from minus infinity to infinity, you get 1. Okay. So if we're dealing with multiple variables, we instead use vectors now to represent our mean and covariance matrices. So the mean is defined to be the expected value of our random vector. So it's mu1 through mu d. And the covariance we write out as this outer product between x minus mu and x minus mu transpose. So if we were just to focus on one of these terms up here, this is actually equal to the expected value of x1 minus mu1 and that's just equal to the variance of x1. Similarly, we can do this for every single entry. So now we have a covariance matrix because we have to express how each of the random variables affects the other random variables. So in general, we have like expected value of x sub I minus mu I times xj minus mu j. And this is a covariance between xi and xj. The key property here is that once you know the mean and the covariance of a distribution, you uniquely specify the multivariate Gaussian distribution. So in general, any distribution you have with multiple variables, you can compute its mean, but only the Gaussian has this property that it's like uniquely determined by the mean and the covariance. The probability density function of the multivariate Gaussian is roughly analogous to the univariate one. So now we have this mess of symbols, but each of the terms is roughly corresponding to the terms from this earlier expression. So if you take the n equals 1 case, for instance, the sigma matrix ends up, the sigma inverse matrix ends up just going in the denominator. So we would just have a sigma squared term here. And then we have an x minus mu squared up here. So in the scalar case, this is like a strict generalization, and that holds for the n equals 1 case as well. But in the more general case, we have to picture this matrix here. And basically how this matrix behaves is how the multivariate Gaussian distribution is actually specified. So that's why we went through all the work of like dealing with eigenvectors, eigenvalues, and trying to understand what the contour plots mean. You can picture what's going on here, where in multiple dimensions, we have this bump where the mean is. So this is where the mu is. And then how spread apart you are in each direction is determined by the covariance matrix. So there's two potential ways to visualize this as well. Any questions here? Okay, so the one other thing I guess we should discuss in relation to this multivariate Gaussian is normally when you're dealing with single-variate, univariate Gaussians, we often compute something called the z-score, right? So we have z equals x minus mu divided by sigma. And then we have this table potentially to figure out confidence intervals and that sort of thing. And that's because any normal univariate distribution you can think of as starting from a normal standard unit normal distribution with mean 0 and variance 1, and you can shift it by mu and stretch it by sigma. So if you're given a new distribution, it's actually just going to be exactly equal to the original standard normal, shifted and scaled. So for instance, the red curve is the standard univariate normal distribution. If you look at this blue curve, it's scaling the variance. So in general, sigma squared is a variance, and sigma we refer to as a standard deviation. If you apply a variance of 5, it's as if you're stretching out everything by a factor of 5. And then mu equals minus 2, sigma squared equals a half, means you're shifting by 2 to the left and then scaling everything by a factor of a half. So that's how Gaussians scale in the univariate case. In the multivariate case, it's actually the mean ends up being shifted. So the mean, you don't have to do anything too special about it. But I guess the covariance matrix, we're going to end up applying this rule here. And the covariance becomes S times S transpose instead. I think we can revisit this a bit later, but basically the idea of shifting and scaling should hold. So in pictures, you can see what goes on here. So in the middle picture, what we're doing is we're scaling all the eigenvalues by a half, which means for each of the directions, we're not moving quite as far. So the density becomes more concentrated around the mean. In the rightmost picture, we're scaling it by a factor of 2. So now everything becomes more spread out, and things are normalized to equal 1. And you can also scale the directions differently. So if sigma equals 2, 0, 0, 1, that means we scale the first direction by a little bit more. So you end up with a contour plot that's scaled more in this x direction. Yeah, I think in the remaining time, let's actually work through one more example, which sort of ties together a few of the topics we've seen. So let's revisit linear regression, and then we can cover some of the remainder math details for the Gaussian next time. So we're going to take a probabilistic interpretation for how linear regression works now. Previously in the past, we had this trading set of xt examples, and we try to form a linear model that tells you how x gets mapped to t. We have a squared error loss, and we can potentially apply L2 regularization as well. And then we basically had two ways to solve the equation. We have a closed form solution, and then you can also do gradient descent to try to figure out what your optimal parameters W are. So this is actually W star. Yeah, so we'll try to give linear regression a probabilistic interpretation now. And what that means is we can assume a Gaussian noise model, meaning you assume each of the samples we get are formed by applying a linear transformation to the inputs plus some Gaussian noise. And that's how t is generated given x. So if you take this probabilistic interpretation, we can use our framework of maximum likelihood and posterior probabilities to try to solve the equation. So maybe take 2 minutes to figure out how you would write the likelihood of t given x if you were to use this Gaussian interpretation instead. Okay, let's just go through this exercise together. So right now we're going back to our framework of maximum likelihood, which is nice because it's a two-step procedure where we first write down our probability expression, and then we try to maximize that expression, right? So here, the data we have, rather than temperatures or heads and tails flips, is instead this data set of x and t pairs. And we're making this underlying assumption that t is generated by x through this normal transformation. Okay. So what we want to do is we want to write out the likelihood of our data set. It's going to be I equals 1 to n. And we have to write out like the formula for the Gaussian here. So each term is sort of asking like how likely is Ti given normal W transpose xi. So one assumption we're making here is the variance is the same for every single data point. So if you were to write this out, we have T sub I minus W transpose x sub I squared over 2 sigma squared. Does the first term make sense? Like, that's the likelihood of Ti given a mean of W transpose x sub I. Yeah, sorry, I keep missing the negative. Yeah. Okay, so we're trying to maximize this expression, and a lot of the math is exactly the same as what we had in our very first example, right? So if you take the log of this entire expression, we have the likelihood of our data given W is equal to, so we're taking the argmax over W now, which means we can throw away the constants that we don't care to estimate, equals argmax over W. We have minus and finally, if you're trying to maximize with respect to W a negative expression, we apply the trick we did before, where it's the same as minimizing W I think the equal sign should go before here. But what is this? Oh, sorry, I should pull this. This is good. What does this expression remind you of? Like if we're trying to find W that minimizes the sum of squares of targets minus W transpose X. Yeah, it's actually going to be exactly the cost function we had before. So this is like a probabilistic way to derive the least squares objective. Because, yeah, I guess if we were to be more concrete about these terms, this term is the target, and then this is our prediction. So this is a cool way to show that when we were doing least squares before, what we're implicitly actually also doing is assuming there's an underlying normal distribution that parameterizes each of the target points, and then basically we're minimizing this expression to find the most likely choice of W. So one other thing we can do here is we also talked about the posterior, and you can also consider just adding a posterior term to our likelihood expression. So what that means is if you consider L of D of theta times L of theta, or I guess some prior belief on what theta looks like, if we choose L of theta to be equal to a Gaussian, like a random variable that's centered at a Gaussian random variable centered at 0. Let me make sure I'm consistent with the slide notation. So if we added a term corresponding to W squared times some constant, which is like our prior on what W behaves like, if you carry out this term throughout the optimization process, you'll end up getting a plus W squared term here. And essentially what ends up happening is you're going to end up with a regularized least square objective. I think I need to be a little more careful with the symbols to make sure the constants work out correctly. But the intuition here should hold. I'll check before next time. But basically the overall overarching point here is if you choose a prior distribution over what your parameters look like, which is W in this case, and you use the posterior maximum posterior approach, you'll end up getting a regularized least square problem. So adding a prior is roughly equivalent to applying L2 regularization in this case. I think the example in the slides is using multivariate Gaussians when it's doing the posterior, so it ends up looking a little bit more complicated. But I'll figure out how the univariate case works. Any questions here? Yeah.
So does that mean, like going back to what you said before about if we have a big enough data set, then the prior doesn't matter anymore? So does that mean with a large enough data set, the regularization doesn't matter as well?
Yeah, that's true, right? So if you have a lot of different data points in a regression task, you're going to put less emphasis on the prior. The prior is saying you should stay close to 0, like we're assuming the weights are normally distributed around 0. But if you have a lot of data points, it's saying we're going to place less weight on that prior assumption.
So does that mean like if we know the data set is really big, then we just can't say we're not going to regularize that, regularize that because like it's basically useless?
Yeah. I guess the big level picture from before is sort of if you have a lot of data, that helps reduce the likelihood you overfit to that data set, right? Because you have enough data that you won't overfit to any particular example. And under this probabilistic interpretation, what's happening is the data overwhelms the prior, so we're just taking into account the data itself. Okay, any other thoughts, questions? Okay, let's end here for today and then resume next time.